Okay, today we're covering 5.5, which is performing function operations. So there's several different operations on functions. They're pretty much just as they show. The only one that we have to be careful of is division, because that can really change the domain more so than the domains we see otherwise. So one important thing to note is that the domains of sum, difference, product, and quotient functions consist of the x values that are in the domains of both the original two functions. So, but then the quotient we have to watch out for, because you cannot divide by a 0. And so that's going to limit it a little bit further if the original domains don't take care of it. So let's try a few and see what we mean. Okay, example 1 is adding two functions. So they're asking us to add f plus g of x. So that's basically function f plus function g. Another way to write this is that you're going to do f of x plus g of x. So to do that, we're going to do the cube root, or I'm sorry, not a cube root of x. Apologize, I read that wrong. We're going to do 3 square root of x, that's f of x, plus negative 10 square root of x, that's g of x. And 3 square root of x minus 10 square root of x is negative 7 square root of x. So f plus g of x equals negative 7 square root of x. Now, the domain is the domain that is true for both functions. So both functions have a square root, and remember, square roots have to have x values that are greater than or equal to 0. So that is the function in the domain. Now, when they want you to find the sum, evaluate the sum when x equals 4. That looks like this, f plus g of 4. And essentially, you're just going to plug the 4 in for x anywhere you see it on the new combined function. And so then we get negative 7, and then the square root of 4 is 2. So negative 7 times 2 is negative 14. And that would be our solution for evaluating the function when x equals 4. Okay, let's try another one real quick. So f plus g of x is the same as taking f of x plus g of x. So we're going to have 5 square root x plus negative 8 square root x, which we then find out is 5 minus 8 is negative 3 square root x. Okay, now it's domain once again, because it's a square root, x has to be greater than or equal to 0. And then when they want to know what the sum is, when x is 16, you can show it like this, saying f plus g of 16. So basically, you just plug in 16 wherever you see x on the new function, and you get, let's see, negative 3 times 4 is negative 12. Okay, let's look at subtracting. So subtracting we need to pay just a slight bit more attention to. So when we're subtracting here, it says f minus g of x. That's the exact same as taking f of x minus g of x. You can look at it either way. So f of x is 3x cubed minus 2x squared plus 5. And then be careful on this. When you subtract, you're subtracting all of g of x. So make sure to put g of x in parentheses, because you are going to have to distribute that negative. All right, so what ends up happening is we have the original f of x, nothing's changed there, but we need to distribute this negative to everything. So we get minus x cubed plus 3x squared minus 4x plus 2. So then we simplify this. All right, so we have 3x cubed minus x cubed, that's 2x cubed. And then negative 2x squared plus 3x squared, that's plus x squared, minus 4x, and then 5 plus 2 is plus 7. So now the domains on these can be all real numbers, because both of them have no limitations if you look at the original functions. So I'm going to put the symbol for all real numbers as the domain. And then it says evaluate the difference, so that's what we're doing here, when x is negative 2. So let's go ahead and plug in a negative 2 in there. So when you see the notation like this, it just means to plug in negative 2 into the combined function of f minus g. So we're going to go ahead and just plug in negative 2 everywhere we see an x. And from that point, we can use mental math or a calculator, and we're going to find out that we get the answer of 3. So our equation has a domain of all real numbers, and when we evaluate the new equation when x is negative 2, our solution is 3. Okay, let's go ahead and let's look at example 3. So multiplying two functions. When this says f times g of x, that's the same as saying f of x times g of x. So we're going to have x squared times the square root of x. Now this can be simplified. X squared, and then the square root of x is the same as x to the 1/2. Now since these have the same base, you can add the exponents. So you can have 2 plus a half, so that becomes x to the 5/2. Okay, so we can write it like that, or we can also write it as the square root of x and then to the 5th. So I'm going to go ahead and just leave it as we have it. So f times g of x equals x to the 5/2. Now remember, the domain that we're supposed to use is the domains of both f and g. It has to satisfy both. So x squared doesn't have any limitations on its domain, but the square root of x must be positive. So that means that we have to limit it as much as needed to make it work for both functions. So that means we have to have x greater than or equal to 0. Okay, so now it wants us to evaluate the product when x is 9. So we have 9 to the 5/2. Remember, that's the same as the square root of 9 to the 5th. The square root of 9 is 3, and 3 to the 5th is going to be 243. So that's our solution for that question. Okay, let's go ahead and take a look at example 4. All right, so on example 4, that's where we're dividing two functions. So that's going to be when we see f divided by g of x, that's the same as f of x divided by g of x. And then we need to state the domain. So we're going to have 6x divided by x to the 3/4. Now remember, 6x is like x to the 1. So one thing that we can do is we can subtract the powers. So 1 minus 3/4. We still have that 6 just hanging out there. So we get 6, and then x to the 1 minus 3/4 is 1/4. So we can write it like that. And so I'm just going to put f over g of x equals 6x to the 1/4. Okay, now when we're looking at the domain, we have several things to keep in mind. So the first thing we have to keep in mind is the domain of the original functions. So f of x, the domain, it was just 6x. So the domain is all real numbers, meaning all numbers are fine. On g of x, that was x to the 3/4, so it had a 4th root. So that means its domain had to be greater than or equal to 0. So when we're thinking about that, we need a domain that is going to, like, it has to be the most restricted as necessary to make each of these functions work. So from there, I think, okay, I need to do x is greater than or equal to 0. But the other thing I also have to keep in mind is that I cannot have g of x be equal to 0 because it is on the bottom of the fraction. It's in the denominator. So I can't plug a 0 in down here. So not only is it that x can't be equal to 0 because that would be the domain for x to the 3/4, we also have to have it not be 0 at all. So it needs to be that the domain is x is greater than 0, not greater than or equal to 0. Okay, and so then to evaluate the function when x is 16, I'm just using kind of the correct notation here so that you guys see it more often. So that's the same as 6 times the 4th root of 16. 4th root of 16 is 2, and 6 times 2 is 12. Let's try another of those division ones. I think they're the more difficult of the ones that we're looking at today. So f divided by g of x, we're just going to take f of x divided by g of x. Okay, and remember once again that I can go ahead and just keep the 4 and then subtract the exponents, so 1 minus 2/3. So I end up with 4. And then x to the 1 minus 2/3 is 1/3. So I'm going to have f over g of x equals 4x to the 1/3. Okay, now let's talk about the domain because I still think that's the most difficult part. So the domain of f of x, which is just 4x, so think about that. That's just a line. The domain is all real numbers, so no restrictions there. Now g of x, okay, and the domain, because it is a cube root, is all real numbers, so no restrictions there. But remember that g of x cannot equal 0 because we're going to be dividing by it. So basically we have all real numbers except x equals 0. So we might just make a note that domain is all real numbers except x equals 0. So basically it can be any number other than 0. All right, and that's that function. And then once again, to evaluate it, we're going to have f over g of 27. So that's the same as 4 times the cube root of 27, which happens to also be 12. Okay, example 5 is solving a real life problem. This is our final example. So it says for a white rhino, heart rate R is beats per minute, and lifespan S, and S is in minutes, so talking about their lifespan in minutes, not just days, years, hours. And that can be related to their body mass, M, which is in kilograms, by these two functions. So it wants us to find R times S. So first of all, before we start, let's just look at what they mean. So if we're looking at their rate, it's beats per minute based on their body mass. So like this heart rate is going to end up being beats per minute. That's what the R of M is going to be. And S of M is going to be their lifespan in minutes. So it's going to tell us how many minutes the white rhino will live based on how much it weighs. So, okay, if we multiply these, that part's fairly easy to do. We're just going to do R of M, which is 241 m to the negative 0.25, times S of M, which is 6 times 10 to the 6th, that's just scientific notation, m to the 0.2. Okay, so what I'm going to do to make this simplify down, the first thing I'm going to do is I'm going to take the 241 times 6 using a calculator. So I can do that and I get 1,446. And then I still have times 10 to the 6th. Now I also have that m to the negative 0.25 times m to the 0.2. So since they have the same base and they're multiplying, you can add the exponents. So that gets me m to the negative 0.5. Okay, and then I'm just going to go ahead and turn this into scientific notation. So how I do that is I actually just look and I would need to move my decimal place back 3 places to be 1.446. Now if I move it 3 places, that means instead of 10 to the 6th, it now needs to be 10 to the 9th. To account for those 3 extra places, I moved the decimal. And then I'm just going to leave that as m to the negative 0. And I totally just realized that should have been 0.5. Sorry about that. And remember, where I got that 0.5 from is I did negative 0.25 plus 0.02. And that's where I should have gotten, totally my bad on that, negative 0.05. And honestly, that's really how I would leave my equation. I wouldn't go ahead and move that m to the bottom, but that would be what I would be looking for there. And then logically, a rhino can't have a negative body mass, so m would have to be greater than or equal to 0, just logically. So it wants to know what R times S of M represents. Well, keep in mind, that's why I had us write the labels above it, because I think it helps look at that. We're taking how many heartbeats they have per minute times their lifespan in minutes. So think about it like this. Beats over minutes, right? And then we're finding their lifespan in minutes. And so that's in minutes. So what we end up with is we're basically finding out the total number of heartbeats over the lifetime of not just any animal, specifically of a white rhino, and the variable m is its mass. So let's say, how about with body mass m? So we have a reference of what everything is doing.